Hi guys, Sajjad Hussain again with a new video. In this video, I am going to calculate the wind loads manually. For that, I shall be using this guide to the use of the wind load provisions of ASCE 798. Actually, I shall be using the example from this guide, but I will not be using ASCE 798. It's a very old code. Rather, I shall be using ASCE 716. Now, ASCE 716 provisions shall be used for the same example. So let's go back to the example. Examples are given in chapter 3. This is the first example, example number 1. This example 1 is a 30 feet by 60 feet by 15 feet commercial building with concrete masonry unit walls, CMU walls. In this example, wind pressure for a typical load bearing, this is a load bearing, one-story masonry building are determined. The building data are as follows. The location is Corpus Christi in Texas. The topography is homogeneous. Terrain is flat, open terrain. Dimensions of the building are 30 feet by 60 feet by 15 feet. The framing system is walls are CMU on 3 sides. Steel framing in front with glass. Open with joist, 30 feet span, and they are spaced at 5 feet on center, covered with metal panel to provide roof diaphragm action. The roof metal panels are 2 feet wide by 20 feet long. Doors and glass size vary. Glass is debris resistant. The building is shown here. In this direction 30 feet, in this direction 60 feet, there is a gate shown and the height is 15 feet. The wall is CMU wall. The framing system is an open joist framing system, and these are the roof panels which are spanning in this direction. They are 2 by 20 feet long. So in this example, the analytical procedure of ASCE 798 for rigid building of all height is used. The same building is illustrated in example 2 for simplified. When we will discuss this simplified procedure, we will take this example again. But for the time being, we are going to use the analytical procedure of ASCE 798. The wind speed as per ASCE 798 is 130 mile per hour. This is given. Exposure condition is C. Building classification is a category 2. And velocity pressure is computed with the very famous formula QZ is equals to 0.00256 KZ into KZT into KD into V square into I. Now, when I am going to use the same building for ASCE 716, so what I did, I just checked the latest velocity provisions for this area. So for that, the site is ATC hazard by location. Site information is given over here. So from this site, I downloaded the information about the wind load. And at this site, ASCE 705, ASCE 7010 and ASCE 7016 wind loads are given. Of course, ASCE 798 wind load is not given because ASCE 798 and ASCE 2005 is the same. Here, the wind speed is given as 125 miles per hour. And for category 2, now as per ASCE 710, when the risk category is 2, the wind velocity is 144 miles per hour. And ASCE 716 also recommends for risk category 2 the wind speed as 144 miles per hour. Now the question is, what is the difference? What is the difference in ASCE 705 provision, 7010 provision and 716 provision? Let me explain one thing. ASCE 798 or ASCE 705, they are based on wind definition as a service load. Yes, let me repeat. Wind load up to the definition or provision of ASCE 705 was treated as a service load. Then from ASCE 710 onward, that means 710 and 716, the wind load is revised as ultimate load. Because of that, before the wind velocity was less, now the wind velocity has bumped up from 125 to 144 for category 2 buildings. So this, if we check, so 144 divided by 125 is something around 15% higher wind is there. So what is the impact? Because of that, in load combination, the coefficients are changed. Let me show you. In ASCE 705, for the load combinations, we can see here article is 2.3, combining factored loads using strength design. In this case, you can see that the wind is multiplied by a factor, but earthquake factor is only 1. Wind is multiplied by a factor of 1.6, but wind is only 1. So this shows that up to ASCE 705, the wind load was defined as a service load, not as an ultimate load. Because in allowable stress design, you can see wind has a coefficient of 1 only, whereas earthquake is reduced by 0.7. Now in 2016, we can see load combinations for strength design. Now wind is 1, wind is 1. And now wind is reduced by for service load combination, the wind is reduced. That means the whole concept of wind definition is changed from ASCE 705 to ASCE 710 and onward. Since we are following ASCE 716, so now our wind load is an ultimate load and our load combinations are totally different. So there are several differences, or the impact is there. For example, the value of importance factor is changed. Now the value of importance factor is 1, and there are other changes also. So let us go back to the problem and let us define our wind load provisions for this structure. For that, what I have done, I used my MathCAD and I tried to calculate the wind load manually. So this is the same example. Let me zoom it so that it will be very clear. So this design example is 30 feet, 60 feet by 15 feet, commercial building with CME wall, the same figure I copied over here. Design criteria, of course, I did not change anything. The only thing is ASCE 716. Now I am following to define the wind load on this building. Since I am not going to design or analyze this building, I am just going to demonstrate you how to calculate wind load on this simple building. So that's why I'm not going into analysis portion. Wind condition, the same thing I have copied over here to prepare my report. And here is the summary of wind load conditions. The exposure category is C. And now I am giving the references also, that this is ASCE 716, section 26. Category 2, importance factor is 1. KZT is equals to 1. Now there is a new factor, and that is the elevation factor KE. Before it was not there, and as per ASCE 716, this elevation factor is taken as 1. And of course the formula is the same as before with an inclusion of KE factor over here. So all these references are there. Then I started calculating the wind load. Now wind load is calculated as per ASCE 716. Now in ASCE 716, they have rearranged the whole code. Before, the wind load was defined in chapter 6. Now the wind load is defined in chapter 26, rather 26, 27, 28 and 30, etc. So they have segregated the provisions in various chapters, and it started with chapter 26. So let us start chapter 26 and let us see what are the provisions over there. ASCE 716, and we will go to chapter 26. So it starts with chapter 26, wind loads general requirement. Now this report I liked it very much because it's written in a very, very professional way, I can say, and they are giving the flow chart to guide the engineer to go through the process of wind definition and wind load definition. For example, here it's summarized over here. Chapter 26, the general requirements. It said that use to determine the basic parameters for determining wind loads on both the main wind resisting frame system and component and cladding. These basic parameters are basic wind speed. The definition is given in section 26.5 and the figures are 26.5-1 and 26.5-2. So what we did, we derived or we took directly the wind load from the site. So we are not following this figure. We have the exact value for this location. Wind directionality factor KD defined in section 26.6, exposure 26.7, topography factor is 26.8 KZT, ground elevation KE, it is defined in 26.9, velocity pressure section 26.10, gust factor 26.11, enclosure classification is 26.12, and internal pressure coefficient, that is GCPI, you can see in section 26.13. So that means now a very systematic way is presented and all the steps are listed over here. So once you define the general requirement, then you go in either of two ways. Either you are applying the load on main wind resisting frame system, or you are defining wind load and components and clouds. Cladding and components. If you are going to define wind load for main frame resisting system, so the first chapter is chapter 27. Here is directional procedure for buildings of all height. Now they have changed the name also. Now directional procedure here in 27 is the same as before. It was called analytical procedure. That was method number 2. In chapter 28, envelope procedure for low-rise building is defined. This is the simplified method. Before it was called, up to ASCE 705, it was called simplified procedure. Now it is named as envelope procedure for low-rise buildings. Then chapter 29 is directional procedure for building appurtenances, that means roof, overhangs and parapets, etc., and other structures. And the last chapter here is chapter 31, which is wind tunnel procedure for any building and other structure. So we are not going to chapter 31 and its provision because we don't have any wind tunnel. We will be following here chapter 27, that is the directional procedure for buildings of all height, because in the guide it is said that for this example the analytical procedure for ASCE 798 will be used. So that's why we will be following directional procedure for buildings of all heights. That means we will be following chapter 27. Now, as you know, the walls are CMA wall. The roof is made of truss. So the main wind resisting frame system is not there. So the walls are treated here. The wind load on the component and cladding may be determined by chapter 30. And in chapter 30 there are 5, 6 or 7 procedures are there. That means envelope procedure in part 1 and part 2, or directional procedure in part 3, 4 and 5, and for overhang etc. part 6, and for non-building structure chapter 7. So for the time being we are not discussing all these. We are going to use part 1 because this is for low-rise building. If we go to part 3, which is directional procedure, and logically it looks that we should go to part 3, but then the limitation is height is there. I'll show you. If we go to chapter 27, so here is the wind load definition for directional procedure, and for chapter 30 we can go directly to chapter 30. This is for components and cladding. Now here you can see, very interesting. The first part is low-rise building. User note. Use part 1 of chapter 30 to determine wind pressure on component and cladding of enclosed and partially enclosed low-rise buildings that have roof shapes as specified in the applicable figure. The provisions in part 1 are based on envelope procedure with wind pressure calculated using the specified equations as applicable to each building surface. For buildings for which these provisions are applicable, this method generally is the lowest wind pressure of all analytical methods contained in this standard. So this is part 1 for low-rise buildings, and this is based on envelope procedure. If we go to part 2, this is again low-rise building, but then it is called simplified. So here is the difference. So we will not be using this simplified procedure, rather we will be using for analytical procedure. So we shall be using part 1, which is directional. Actually here is a bit confusing. I can understand that maybe it's a typo error, maybe in the next edition they will change that this is for analytical procedure, or they call it directional procedure. So that's why we shall be using part 1, not part 2. And in part 1 we will be defining the load on walls, and here is the condition that the design wind pressure on component and cladding elements of low-rise building and buildings with height less than 60 feet shall be determined from the following equation. This is the equation, and it says that figure 30-3-1 shall be followed for the walls. Anyway, when we will go into details, so we will be following this one. Now let's go back to my manual calculation. As I explained all this flow chart, here I'm just comparing whether I can use the directional procedure or envelope procedure. So it says that wind load shall be calculated using the table of ASCE 716 for directional procedure, because it is given in our example that we should be using analytical procedure, so that's why I shall be using directional procedure. Although it qualifies for envelope or simplified procedure, because the mean height is less than 60 feet, is simple diaphragm building, because the roof will behave as a diaphragm. It's not a flexible building. It's made of CMA walls. It does not have response characteristics requiring special consideration. Yes, that's correct. And it is a regular shape and symmetrical cross-section building. So all the parameters which are required to qualify for envelope procedure are there. But for demonstration purposes, we will not be using the envelope procedure now. Maybe later on in another video I will cover that aspect, but for the time being we are using directional procedure. So we know that this is a regular shape building, there is no unusual geometry, etc. We know that the wind speed is 145 miles per hour, exposure category is 2, importance is 1, occupancy category is 2, and exposure is C. So first I'm going to calculate the wind force calculation, say in north-south direction. That means normal to 60 feet. Let's suppose the wind is blowing in positive y direction. That means when I'm going to model this building, and I shall be applying this wind load in SAP2000. So if we see the building back, if we see this building back, this building consists of these web joists which are 5 feet apart, or this CMU wall. But for the sake of simplicity, what we will do, we will model this building in SAP2000 with frames, because no need to have joists defined, etc. And we will define wall element, and we will apply the wind pressure on these walls. So if the joists are at a distance of 5 feet, that means along this length, which is a 60 feet, and my first consideration is that the wind is blowing perpendicular to the 60 feet face. So that means the wind is blowing in this direction. So as per our sign convention, this will be X, this will be Y, and this will be Z. So along X-axis, the length will be 60 feet, along Y, the length will be 30 feet, and along Z, the length will be 15 feet. Now, since this, let's assume that these are the frames. These frames, they are spaced as 5 feet, so there will be 12 sections or 12 spans over in that direction, and there will be only 2 in Y direction. We need not to define in between, and then in Z direction there will be 2. But there is a but. Well, later on we will be defining the loads on component and cladding on the side walls as it is defined here on the guide. So we will be following the same thing. Design pressure and component and cladding for the wall. So here is the zone 5 and zone 4. So there is a definition of A. So how to define this? There is a condition. This A is 0.1 of H or 0.4 of the least dimension or 0.4 of H. So because of that, the controlling factor here is 3. So maybe we can have some grids over there. So let us start our design. We can proceed like defining the frames along x-axis at every 5 feet, and there are 2 over here. So later on, maybe when needed, we will define the more grids. We'll see. We'll go to SAP2000, new model. The units are kip and feet. No problem. Let's define grids only. In x direction, as we know, there will be 13 grids and the distance between them will be 5. In y direction, there will be 2 grids and the distance between them will be 30. In z vertical direction, there will be 2 grids and height is 15 feet. Okay. So here is the grid system. Let's go in zx direction. Now, since we are not modeling the CME wall as some 2D element or some quad element, or you can say some brick element, etc. So rather to save our time, and just because we are going to demonstrate the way the wind load is applied on this structure, what I am trying to do over here, that I will define frames. Let's take some steel section. Add new property. Let's assume a W section. No, let's import W section. It's a bit slow. Hopefully it should end. I do not know why it's going to take that much time. Something wrong. Let's start again. Anyway, let's go back to our model. So here in this calculation, as you have noticed, that all the parameters are calculated over here. I will be calculating all these parameters, and I'll show you how to calculate all these parameters as per ASCE 716, and from where these values are taken and what is the meaning. Like for example, internal pressure coefficient is said that use GCPI with a plus sign and a minus sign. What does it mean? Why should I use a plus and a minus sign? There should be some reason. Now that is quite interesting, because in wind load the internal pressure is taken as positive and negative also, although this is an enclosed building. What does it mean with a negative sign and a plus sign? That means, if we take this example, this figure, if wind is blowing perpendicular to this 60 feet wide face, there is only door is shown, but certainly in all the buildings there are windows, etc. So if the wind is blowing from this direction, the wind will enter from the doors and windows, etc. So what it will do, it will create a positive pressure inside the building. And if a positive pressure is developed inside the building, so that positive pressure will be exerted on all the walls and roof from inside. So that means that positive pressure will create pressure on all the walls and roof from inside to outside. But suppose the wind is flowing like this and there is no opening on this side, and the wind passes over the building, then on the leeward side there will be negative pressure. And if the building has openings on the leeward side, so what will happen? It will extract air outside, and that will cause a negative internal pressure. So in that case, this negative internal pressure will be acting from outside to inside. That's why both the cases are considered, that for internal pressure, take the coefficient for internal pressure and take the positive side also and the negative side. But do not mix. This is very important. Do not mix the values of positive and negative, because there will be one condition. Either the wind is blowing in this direction and it is going to pressurize the building, or the wind is passing over the building and it is creating some vacuum inside the building. So in that case, it will be negative pressure inside. But it will not be possible that it is blowing in this direction and it is going to create a negative pressure in the building. It cannot produce a suction in the building. So you must understand the concept. The wind is blowing and there are openings. None of the building is 100% airtight. The buildings are porous, openings are there, doors, windows, etc. are there, and the chances are either the wind will enter inside the building or the wind will come out of the building. Hi guys, so let us start again. Actually, there was some problem and my system was hanged. So now I have started again. So here I am going to import some sections. Let us import W sections, all W12 sections. Although that much is not needed, we will be using only couple of sections, only one maybe. Say we shall be using W12 by 72. Okay. So let us define our section. This section is W12 by 72. So here is our beam defined. These two columns are also defined. Now what I can do, I can replicate. Let me select all and then I will replicate. I will replicate in X direction. For every 5 feet, and there will be a repeat of 12 times. So in this direction we have already defined. Now in this direction we can also define the same beam. Sorry. Similarly, we can define the other side. Yeah, from here to here. Oh, sorry. Undo. So the frame is defined. Now let us define the wall. Suppose we are going to define the area section. We can call it wall. Our walls are, suppose, 6-inch thick. Okay, and also we are going to define roof. Let roof also be 6-inch thick. Okay. So now we can define the wall. It will start and it will end over here. So we can see the wall over here. Similarly, we can define the wall over here. And we can define the slab over here. We know that when we will be defining the pressure on the slab conditions are h by 2, then h, and then up to 2h. So it is better we can define the slab into at least 4 segments. Let's undo it. So for that, what we can do, we can replicate this beam for 3 times. In y direction, let's be 7.5 feet, 3 times. Okay. Then later on we will delete these beams. So now we can define the roof. 1, 2, 3, 4. Okay, let us save this file. Save this file. Okay, so we can define these beams which were not needed. Sorry, this beam is not needed, this beam is not needed, and this beam is also not needed. Hopefully that beam is deleted. No, the beams are no more there. Now let's go back to our calculation. We started wind load calculation by defining the required parameters and their reference section, etc. Let's open the chapter 26. For our quick reference. So in chapter 26, as per this flow chart, as I explained to you, the wind speed we have already taken from the website. So here is the wind speed, 144 mile per hour. Occupancy category is 2. Now, wind directional factor KD, section 2.6, 2.7, 2.8, 2.9, etc. So let's go back to 2.6. These are the symbols. This portion has already been selected. We have selected from the website, so we are not using these graphs. Now, wind directionality. It says that the wind directional factor KD shall be determined from table 26.6-1. That is table 26.6-1, wind directional factor KD. Buildings. Main wind force resisting system KD should be equal to 0.85. And here we have selected KD as 0.85. Exposure we have already defined that the exposure categories already defined in our problem that this is reference C, so we will take exposure category as C. Now, as per 2.8 topographic effect, here there are various conditions, but we are not considering any escarpment, either 2D or 3D. So because of that, what we have done, we have selected Kz is equals to 0.85 and Ke is equals to 1.0 and Kzt is equals to 1. All these parameters are defined over here. These are the K1, K2, K3 multiplier, and then Kzt is equals to 1 plus K1 into K2 into K3 raised to power 2, where K1, K2, K3 are defined like this. So all these parameters are 0, so we take Kzt is equals to 1. This is from figure 26.8-1. Now Kz here is defined exposure C up to 15 feet, that's 0.85. Here's the Kzt, and ground elevation factor, it is said that you can take Ke is equals to 1. So having all this information, we can apply these parameters to this equation, which is velocity pressure equation number 26.10-1, which is Qz is equals to 0.00256 into Kz, Kzt, Kd, Kb square. So here we have calculated using the same formula. So our pressure comes out to be 38.353 pound per square feet. Now the same Qz will be equal to Qh in our calculation, and gust factor is here 0.85. If we go to section 26.11, we will see the gust factor is there. The gust factor, it can be taken as 0.85. So we are not doing any analytic. We are not using any analytical procedure. We are just taking the value of gust factor as 0.85. Now, internal pressure coefficient GCPI is plus minus 0.18, and this is from table 26.13-1. Sorry, there is no 17, it is 16. This is the table 26.13-1. It says main wind force resisting system and component cladding for all heights. Internal pressure coefficient, that means GCPI, for enclosed, partially enclosed, and partially open and open buildings. So for enclosed building, we are taking moderate internal pressure, which is 0.818 plus and 0.18 minus. So based on these parameters, we have calculated the this is a replica of our table for importance factors. I have modified the importance factor for wind, which is 1 for building type 2, and for all buildings now this is 1. Now I am going to calculate the design wind pressure for main wind force resisting system, and this is calculated with all these parameters, and here is the equation where P is equals to QH into G into Cp minus QH into GCPI. So I calculated windward pressure for positive GCPI. This is equals to P, because I am using GCPI as plus 115, and for minus I will change the equation with a negative sign. So in that case, for windward wall, here you can see for windward wall, the positive pressure will be equal to 19.177. Now this was the case where wind is blowing perpendicular to the 60 feet wall. That means this wind is blowing here. So let us select the right wall. So here is the wall, and this wind is, we assume that wind is blowing in plus y direction and our Cp is positive. So let us define this force. Define load pattern. We are going to define wind load case, which is in positive y for positive CPI. This type is wind. No, we are not following any standard. It will be user defined. Add new load pattern. Similarly, we will be defining wind load with negative CPI. So for the time being, let us define these two wind cases and let's see what happens, because another direction, this is a replica. Okay. So we are going to apply our windward wall pressure over here. Our windward wall pressure, as we calculated, was 19.177. So the windward pressure is going to act perpendicular to this wall. And now, since we have this wall supported on the columns, or there are columns inside, so what we will try to do, we will try to transfer this wind pressure on the column. How it is done in SAP? Let's see. We will assign area load, and here there are various options. Is a gravity load, is a uniform load on the shell, or it is a uniform to the frame applied on the shell. We will select this one. And our load case is wind is blowing in positive y direction with positive CPI. The direction is positive y. Load distribution is one way, and our load is 19.177. So let's select the proper unit, pound per square feet, and this is 19.177. So this load will be in positive y direction. Let's apply. Now here you can see the value of wind load is given. Let's see, can we display this wind force? So now you can see that the wind force is applied or transferred to the columns. You can note one more thing, that the column on these two extreme ends, their value is half than the middle values. So if we check, we applied a load of 19.177 and the width of the center to center distance of the column is 5 feet. So if we multiply, our value comes out to be 95.885. So this is 95.889 and half of this load is applied over here. That means SAP has transferred the load from the surface or the area to the frame. This is clear. Let us save our model. When we will consider the negative load case, then we will apply this. For the time being, leeward wall. For leeward wall, the CP is minus 0.5 and the positive pressure will be minus 23.204. This negative sign indicates that it is away from the surface of the wall. So 23.204, this force will be applied on the leeward side of the structure, on the leeward wall. So now I have selected the leeward wall. I have selected the wall now. The value is 23.204. I'll assign area load uniform to frame shell. Load case is this, global Y one way. This is 23.204. We will add this value. So now we can display the element force. Yes. Now you can see the leeward wall also have the force which is away from the surface of the wall. Now, before proceeding to roof, let us stop over here. Hi guys, let us continue. So far, we have already defined the wind pressure on windward wall and wind pressure on leeward wall as per our manual calculation. Now let us apply the loads on the roof as it is calculated over here. Since the theta, the slope, is less than 10 degree and h over L is 0.5, so Cp is equals to minus 0.9, and this is applicable from 0 to h by 2, that is 7.5 feet. And positive pressure is, positive means pressure is not positive, that means when GCPI value is taken positive, so the roof pressure comes out to be 36.244 and first quarter of the area of the roof, that is up to 7.5 feet. Then from h by 2 to h, that is 7.5 feet to 15 feet, Cp is again 0.9. That means if we combine these two, then from 0 to h, that means up to 15 feet, the pressure will be 36.244, and it is negative, means it will be upward. So let us apply this force 36.244. So let us select roof. Let us select roof over here. So we have to select first and second row. So this is half of the roof. Here we have to assign area load, then of course it should be wind plus Y plus CPI global. The direction is Z plus, and the value over here is 36.244. So let's apply this load 36.244. It will be acting upward because this is positive, and let us have add to the existing load over here, apply. So now we can see that half of the roof is loaded with 36.244 pound per square foot area load. Let's see over here, display. Yep. So now we can see that half of this roof is loaded and the direction is upward. And for second half, from 15 to 2h means 30 feet, this is 23.204. So let us apply here, assign area load shell, this is 26.204. Okay, so here we can see the load. So now you can see that the windward wall is loaded, leeward wall is loaded, and roof is also loaded. So let's have a better look. So you can see the roof is also loaded. First half of this roof is here and second half is loaded like this. So that means we have applied the loads on windward wall, on leeward wall, and on the roof. But what about side? That's a good question. Here, in this example, in main wind force resisting system, windward, leeward for another direction, and the roof loads are there. So here is the figure shown. This is another direction which we have not considered so far. And then this is now it is started with design pressure for component and cladding. And they are using the similar equation where QH is equals to whatever they have calculated before. Now under component and cladding they are calculating the wall pressure. This wall pressure load is not considered or has not been defined for main wind resisting system. Although the CP value was there, but this is not considered. Why? Because it's a masonry wall and it cannot be treated as main wind resisting frame system. That's why the wall is considered in component and cladding. So now we have also done the same thing. As per component and cladding, we are using part 1 as I explained before, and the values calculated. The wall is calculated as per figure 30.3-1, and here is the calculation. In this figure 30.3-1, the effective wind area is defined as H multiplied by H by 3, which is 75 feet square, and there are different zones. Let's see what is figure 30.3-1 so that it will be very clear. Let's go to 30.3-1, component and cladding. Let's go to figure 30.3-1. So this is the figure 30.3-1, component and cladding for height less than 60 feet, external pressure coefficient, that is GCP, for enclosed and partially enclosed building, and this is for walls. So here are the figures. Now if you see this figure, this is the side wall we are considering, and for side wall the first thing defined should be A here, then area 5 and area 4, where A is defined as it should be 10% of least horizontal dimension or 0.4 H, whichever is smaller, but shall not be less than 4% of the least horizontal dimension or 3 feet. So this condition is applied over here. A is minimum of 0.1 L or 0.4 H, so A comes out to be 3 feet. And then from the figure over here in corner zone number 5, for corner zone number 5, this A is 3 feet, and the positive pressure is here, the negative here. Now this is area. Our area is 75 feet, that means we should draw a line between the two, and then we should take this value and this value and this value for area 5 and area 4. So So imagine that a line is drawn in the mid and the values are read here. So as per this, the positive GCP comes out to be 0.85, and for positive case, when the GCPI also taken as positive, the pressure comes out to be 25.697. So this is the pressure on the wall in zone 5, which is only 3 feet wide. So if we go over here, if we select YZ plane, so this is the YZ plane. Now we don't have any grid over here, so what we can do, maybe we can offset this for 3 feet, replicate in y direction minus 3 feet, and there should be only one. Okay, and from this side this should be replicated for plus 3 and only one time. So this is zone 5. So let us define the area. It's not roof, it's wall. This is zone 5. This is zone 5, and here is zone 4. Right? We can select this and we can replicate it at this side. So let us replicate in x direction at 60 feet. Y should be 0, only one time. So we have defined the wall on both these sides. Now what we have to do, we have to apply in this portion the load. Since this is masonry wall, no need to have this beam, this column over here. Oh, sorry. We can delete this. We can delete this. Okay. So first these two areas, since there are no columns, so we will just define simple load on these walls, and our load shows here 25.697. So on this face, this will be negative x direction. Let's assign area load uniform plus CP. This should be minus 25.697. 25.697. So we have applied 25.697 here, and here for area 4, zone 4, it is 25.697, the same thing. So let us apply here also. Assign area uniform load minus there was a mistake. We will okay, cancel, close. So this is assign area load shall replace, this is in x direction minus 25.7, apply. Now this is correct, and when we will go to the another side of the wall, this force will be positive. So let's apply assign area load uniform. Now it should be positive. Apply. So let us save. So now this concludes the application of load on a closed structure when the wind is blowing on the larger side. Similarly, we can repeat the same calculation, although it has been repeated. I have done the same thing. When the wind is at normal to the 30 feet side, that means when wind is blowing in positive x direction, then we can do the same thing. We can calculate the wind load on windward side. In that case, the windward side will be this face, leeward side, this face, and side wall and the roof, etc. Similar procedure can be used, and the structure should be loaded like this. Not only that, we have to consider the wind blowing in plus x direction, but we have to also consider that the internal pressure, it should also be considered positive and negative both, because as I explained, there are chances that the internal pressure developed will be positive or internal pressure developed will be negative. Since we do not know, so we have to consider all the possible load cases. So I think here I can conclude my video. Hopefully it will make you understand that how do we calculate the wind load manually for this structure. This is the first example. In this example, I defined the wind load as per ASCE 716, and the method used was directional method. Now for the second lecture, maybe I will develop for the simplified procedure, or they call it here the envelope procedure. So I'll show you what is the difference. Now in this case, what we have done, let me summarize. First, we defined the wind parameters as per chapter 26. Then we defined wind load for main wind frame resisting system, and for that we followed chapter 27, and for component cladding we have followed chapter 30. In this book which I selected, there are so many examples. Basically, this is a very comprehensive book. Various examples, there are 10 different examples. I'll try to go one by one. Like for example, this second example is using the same building but with simplified procedure. Then third is a different building, which is a high office building where height is 160 feet, so there is a different condition. The same office is used and located on an escarpment. So we will study what is the impact of height, what is the impact of local topography, and there are different type of houses. For example, 2,500 square feet house with gable or hip roof, and the same is used for isolated hill, etc. Another one is a gable roof for commercial warehouse building using all height provisions. And same building example is revised with a low-rise building provisions. Then commercial building with monoslope and the billboard sign, etc. So I will try to develop manual calculation as it is given over here, and I will try to explain how it should be done in the light of latest code, which is ASCE 716. And as I explained to you, ASCE 716 is based on ultimate load definition of the wind. So hopefully you will like my video. So for the time being, I am going to conclude my video now. Thank you very much. Hopefully you will not forget to subscribe my channel. Bye.